Hello everyone. Let's continue to plot the VIL and all the voltage levels that we have attained in this particular graph onto this particular scale. So what we are trying to get over here is we are trying to get the noise margins. So noise margin will basically define the input voltage range and the output voltage range, and basically where your input voltage should lie and so on things. So let's try to plot this, and then it will make more sense to look at, to talk about the noise margins. So first of all, let's just plot this particular curve. Let's forget about noise margins, the terms and all. Let's try to plot this particular voltage levels on this particular scale. Okay, so the first comes, if you look into VOL, VIL, VIH and VOH, the highest of it that we see over here will be VOH. And why so? Because we know that VOH will be greater than VIH, and the reasons we discussed in the last video, where we said that the VOH has to be always be greater than VIH so as to be detected as logic 1 to the next stage of the input. Okay, so this particular inverter will be connected to some logic. Okay, and the output high voltage which is present over here, that should be somewhere greater than VIH, so that the next stage will detect that particular voltage level as logic 1, because any input voltage which lies greater than VIH will be detected as logic 1, and so VOH will be greater than VIH. So let's and which makes it very close to VDD. Okay, so let's plot VOH first. VOH lies somewhere over here, and after VOH you have the next highest value, which is VIH. Okay, so let's plot the VIH over here. Next we have some area over here which is undefined, which is there is no voltage levels in this particular area. And then next voltage level that we have is directly the VIL. And again, why the VIL and not VOL? Because of the same reason, that VOL will be lying somewhere in this area. And the reason for that is the same. If this particular inverter is connected to some other logic, the output voltage of this particular inverter should be somewhere less than VIL to be detected as logic 0 by next stage. And something which is less than VIL is VOL, the output low voltage, the lowest voltage which is present at the output of this particular inverter should be less than VIL. And as a result of that, VIL will be greater than VOL, and it is the next voltage level after VIH which is present over here, if you go by a descending order. Okay, so let's plot VIL over here, and the last one which is VOL. So now we have got some well-defined values over here. Since we have got some well-defined values, and this goes as a part of the specifications of a chip. Okay, so we have these well-defined values, and let's talk about the value which is which we have at the output. So this particular range of the logic 1 will be called as noise margin high. So noise margin high says that any voltage level, whether let it be present at the input or the output side, any voltage level which lies in the range of VIH and VOH will be detected as logic 1, whether it be present at the input or at the output of the circuit. This is basically noise margin high. Next we have the range which is present over here, for example this one. So this says that NML is the noise margin low. It says any voltage level which lies in the range of VOL and VIL, it could be at the input or the output side, will be detected as logic 0. Okay, this is what noise margin low says. Okay, and noise margin high, the equations for noise margin high and noise margin low are very simple. The noise margin high is nothing but the VOH minus VIH. The noise margin low is VIL minus VOL. Okay, so this is what the voltage level should be. Under an ideal condition, the voltage levels can't be exactly equal to VDD or exactly equal to 0. There are power related issues, there are crosstalk related issues, so there should be a range, there should be a certain range. And also, if you see some bump, for example, as we'll be going further, we'll be talking about bumps and all. So as you see, if there are some bumps over here, those bumps, if they lie in this tolerable range, so these are basically range which are tolerable to noise. Okay, so if the bump levels, we will be talking about more of bumps in the upcoming videos, but if the bumps lies in this range, if the noise that is induced lies in this range, or if the noise that is induced lies in this range, it won't harm your circuit, because it will be still detected as logic 1 or logic 0 without harming any of the functionality of your circuit. So that's a margin that we have, and that those kind of noises could be easily could be easily eliminated or could be easily ignored at that point of time. Okay, so that's what we are going to that's why this particular topic of noise margin is pretty important, because we will be determining the voltage levels of the bump, and based on the voltage levels of the bump will be determining whether that particular bump is is a harmful bump, or it's a one which can be ignored. And there are other factors also that decides the noise. For example, there is the noise width and all those things. We'll be learning about that in the upcoming videos. But this particular noise margin are the nothing but the tolerance levels of the noise. This decides your tolerance levels of the noise. So we have a chart based on the tolerance levels. But before that, if you see somewhere over here, if you see this region between VIH and VIL, this is nothing but the undefined region. So any bump which will lie in this area, the, that will go into an undefined state, which says that it can be either logic 1 or either logic 0. So with this particular scale, the voltage level which is plotted in this particular scale, with that scale in mind, we have prepared a chart which will give a summary of noise margin. So for example, this was the scale. It has got the noise margin high, it has got the noise margin low, and this is the voltage curve. And noise margin high is nothing but VOH minus VIH. Noise margin low is nothing but VIL minus VOL. And anything in this range, so we have plotted this ranges over here, which says that anything in this range will be determined as logic 1, anything in this range will be recognized as logic 0, and anything which lies over here will be an undefined region. So by undefined region, what we mean is this one. So let's start with the low bump first. So for example, if you have a bump in this area, if the bump height lies in this particular area, it's not hazardous for us, because it still lies in the range of logic 0, and your logic will be still kept as logic 0. It won't harm the circuit. That's what this particular bump means. Okay, so we will be seeing this kind of bumps in the upcoming videos. Where are this kind of bumps getting created and all those things? Basically, this is nothing but your glitch. So glitch height, if it lies in the range, and for example, if there is a net that was very steady, that was continuous at logic 0, and due to some reasons it gets a glitch, and if that particular glitch lies in this range, it's still a safe glitch. Okay, next, if there is a glitch which is of this height, if there is a bump which is of this height, if the bump height lies in this undefined region, then as the name suggests, it's undefined, so we don't know whether it will go to logic 1 or it will come back to logic 0. So basically it's an undefined region. So these are basically unsafe glitches that we have, and this needs to be fixed. Okay, and there's a third case where you have a bump which is pretty large, and the bump height lies in the range of nmh. In that case, that will definitely go to logic 1. That will definitely treated as logic 1, and there are other disadvantages of having it. There are other harmful effects of having this height of bump, and these kinds of bumps are the ones which needs to be fixed. Okay, so now that we know the definitions of noise margin, the NMH and NML, the next step is to evaluate NMH and NML based on the CMOS inverter that we have been using till now. So let's try to start from that point in the next video. Thank you.